Kia ora Year 13. This video is going to be going over the basics of the binomial distribution. So this is mainly for the 7 of you who will be in class today. Today is Wednesday of week 1 term 3. So make sure that you've read also the ESA workbook on pages 199 and 200 for a more thorough discussion, and we'll go over some of this in class. So the distribution we're looking at here is an example of a discrete distribution. We talked about that yesterday. We are going to be working with a random variable that we're going to call x. So x is a thing, and in this case x is an event, and it's going to be when I toss a coin, and we'll do it 3 times. How many tails do I get? Right, so you can already see that if we're doing the coin toss 3 times, a binomial situation is made up of a number of trials. Okay, so each toss of the coin is called a trial, and what can happen on each of those trials? Well, we call that an outcome, and there are 2 outcomes, and only 2 outcomes. We can either get a head or a tail. Okay. So these trials are named after a kind of Dutch-Swiss, what happened there? Dutch-Swiss, very, very famous mathematician, who I'll talk about in class, and his name was Bernoulli. He left the Netherlands when he was little and moved to Basel in Switzerland. Okay, so these trials are called Bernoulli trials, and they form the basis for the binomial distribution. What we do is we count up how many times we get a tail, and we call that x. So we're going to work with the coin tossing situation, but we're going to work with a biased coin. We're going to look at how we'd solve this problem using what we learned in probability concepts. So the probability that it lands on tails is only 0.2, right? It works better than doing it with 0.5 to give you the big ideas. So I want us to find out the probabilities that we get 0, 1, 2 or 3 tails in the 3 throws. So forget that you're doing Year 13 stats and think back to Year 12 when we knew all about tree diagrams. So the first time we throw the coin, 2 things can happen: heads or tails. The second time, 2 things can happen: heads or tails. And the third time, we can get heads or tails. So you can see why I picked a nice low number of trials. Have I done that right? Let's see. Okay, now I trust you to email me if you find any bad mistakes. Okay, so what we can do now is we can put the numbers on. So for each trial, we have the probability that it lands on tails is going to be 0.2, and for heads it will be 0.8. I'm going to hammer the conditions of the binomial into your brains between now and November, but you might as well start by noticing that we've got some pretty strong patterns in that tree. Okay, one of the conditions for something to fit a binomial pattern is that these numbers must be the same at every trial. Okay, so we've always got to keep an eye on that. So it's always 0.8 and 0.2. So to figure out the probabilities that we get 0, 1, 2 or 3 tails, then we can do what we always do, and we just go down the tree, and we'll start off by adding up the outcomes. So for the first one, we're going to go 0.8 times 0.8 times 0.8. That gives us 0.512. Alright, the next one will be 0.8 times 0.8 times 0.2. And that will be 0.128. Right? I suggest that you do this as we go in the video. Now, looking at this, we've done the calculation here. We've got, where's my pointer gone? We have got, where's my nice little pointer? Here we are. Right, I'll do there's the lightsaber, right? So this path has got 0.8 here, 0.8 here, and 0.2 here. We've got a couple of other ones that have got those same numbers in them. Okay, so this was H, H, and T. That was 1 tail and 2 heads. I can see that coming up again down here where I've got an H, a T, and then an H, so that next one there is also going to be 0.128. Okay, and then again down here, I've got 0.2, 0.8, and 0.8, so that's 0.128. Right, going backwards to one head and two tails, what's that probability going to be? Well, 0.8 times 0.2 times 0.2. So that's very little, so that's just 0.032. Same thing again here, 0.2, 0.8, and 0.2. Right, so two tails and one head. Whoop, wrong thing. 0.032. This one here, tail, tail and head, also 0.032 or 0.032. And the last one is going to be 0.2 cubed. So that's a tiny probability of 0.008. Okay, so what this hasn't done yet is figured out the answer to the question. So the probability that we've got 0, 1, 2 or 3 tails, what we need to do now is to add up the relevant outcomes. So figuring out the probability of 0 tails is easy. It's just that one, 0.512. The probability of 3 tails is also easy. It's that one there, 0.008. For the in-between ones, so 1 tail, we're going to have to add up this one. Let me get another colour. Right, this one, and this one, because all of those are ones where I have got 2 heads and 1 tail. Right, 2 heads and 1 tail here. What a mess. 2 heads and 1 tail there, and 2 heads and 1 tail here. So what we're going to do now is to write this down as a probability distribution. I'm going to do this on the next slide. Okay, so what did we figure out? Well, the 0 had a probability of 0.512. The 1 had a probability of 3 lots of 0.128. The 2 had a probability, so getting 2 tails out of 3 had a probability of this. And the 3 was also an easy one, so it was this probability. So let's just work out the 2 numbers in the middle. And we get 0.384, and for the next one we get 3 times 0.032. Okay, so 0.096. Right, so that's all very good. Now we've got a probability distribution for our first binomial random variable. But you could see a whole lot of pattern in that tree, and the whole point of having a binomial distribution is that once we've got the situation, we don't need to use a tree diagram again. So now let's take a look at how we can get a pattern and then a formula for binomial probabilities. Well, let's think about what happened with how many of each type we could get. If we're working with the probability that we had 2 tails, oh, I should have started with 0. We'll forget about 0. We'll put 0 down the bottom. There's 0 down there. So the probability that we got 3 tails happened like this. We had one way of that happening. And if that happened, that meant that we had 3 trials where we got a tail. The probability on the tree worked out to be the 0.8 times 0.8 times 0.8. And we had no heads coming up. When we did no tails, we had 1 times no tails and 3 heads. So we had the 0.2 cubed. When I got 1 tail, there were 3 ways that that could happen, because it could be the first, second or third in my experiment, right? So there were 3 ways, and getting 1 tail meant that I had 1 bit of tree with 0.8, and then I had 2 bits of tree with 0.2. When I had 2 tails, there were 3 different ways on the tree for that to happen, and that meant that I had 2 sprigs of tree with 0.8 and 1 with 0.2. I want you to pause the video And now try and write down a formula for if you've got n trials and you've got a probability p of success in each trial. So in our case we had 3 trials, and our probability of success, in other words getting a tail on each trial, is equal to 0.8. So have a go at developing a formula. If you've done level 3 calculus, you're going to spot the pattern going on in here more easily. You're going to spot it even more easily if you put the 0 at the top. Okay, so try that, and it's coming up on the next slide. Okay, before I get to the conditions, let's do the formula. Okay, so the probability that x equals x in a binomial has got 3 bits. The first bit is how many ways are there to have n x objects drawn from n. We know from when we did combinations and permutations that how many ways are there to choose n objects from x is given by n cx. Okay, or remember from Pascal's triangle, it's the numbers from whatever row of Pascal's triangle we had. So we were working with n of 3, so this is the relevant row of Pascal's triangle. There are my 1, 3, 3 and 1 numbers. So that's the first bit. The second bit is what was the probability on each trial of getting a tail. So that was p. And if we had x successes, that means we have p times itself x times. So if we had p, the x was equal to 2 here, we had how many ways to get 2 tails out of 3 trials? We had 0.8 squared, and that left us with 0.2, or 1 minus p, to the power of n minus x. So we've used up 2 out of the 3, so this must be 1. Okay, so that's my formula for the binomial distribution there. There are 4 really important conditions that you need to know for this. Okay, the first one is that it must be, a fixed number of trials. That means that you need to know that you're throwing the coin 3 times. It can't be that you're just going to keep on throwing the coin until you've got a certain number of tails. The second one is that the trials must be independent. Just because you got a tail on one throw can't affect the probability of getting a tail on the next one. There can be only 2 outcomes, or it doesn't work. We can sometimes get around this in harder problems by redefining what we mean as success or failure. Right? And those words don't have anything to do with real life. Success here is a tail, okay, and failure is a head. The probability of success on any trial is p, and that is constant, right? So it doesn't change over time. Now, sometimes people get these two confused a bit, so just watch out, they are different things. I'm not going to go on about that anymore now, but we'll do that as we go in class. Okay, finally, an example for you to try. Right, Count Up sells potatoes. This is inspired by real life, in fact, by tonight's real life. They are all the same size and type. On average, 10% of all potatoes are rotten. What are the chances that if you buy 8 potatoes, 2 are rotten? So we've got n equals 8, p equals 0.1. These things are called the parameters in this distribution. They are the only 2 numbers that you need to know to solve problems in this situation. We're trying to find the probability that x equals 2. So success here is defined as a potato is rotten. Okay, so probably the x equals 2. Well, how many ways to choose 2 potatoes out of 8 is 8c2. The probability, we're looking for 2 being rotten, so it's going to be 0.1 squared times 0.9 to the power of 6. Okay, so that equals 28 times 0.1 squared. I'm just doing it on my calculator as we go. I'll try not to screw this one up, 8.1 squared, right, times 0.9 to the power of 6. Okay, so when you put all that together, you get 0.1488, right, to 4dp, which is what I'd usually do in this topic. Okay, so there's only a 15% chance, or a 14.88% chance, that if you buy 8 potatoes, 2 are rotten. Okay, so obviously I got the unlucky potatoes tonight. That's all for now. There are loads and loads of examples in the book, but we're going to look at how to do these on the graphics calculator very soon in class, so don't go doing too many by hand, and hopefully that all made sense. Thanks very much for watching. Please tell me if you find any mistakes.